Welcome back to the deep dive. If you've been following the LLM space, you know context length is, well, everything right now.
Absolutely. We're seeing models like DeepSeek R1, Gemini 1.5 Pro, pushing into hundreds of thousands of tokens. It's opening up some really wild possibilities.
Things like analyzing huge code bases
Yeah.
or making sense of incredibly long documents,
Yeah.
right? Stuff that was just science fiction a couple years ago.
Exactly. But there's a massive catch. These incredible capabilities run smack into this fundamental barrier in machine learning.
You're talking about the attention mechanism, the n-squared problem.
Precisely. Standard attention, as your context length n gets bigger, the compute cost just explodes quadratically. It's a computational brick wall.
And that's not just some theoretical issue on a whiteboard, is it? It hits hard in the real world, in latency.
Oh, absolutely. When you're actually decoding, say, a 64,000 token context, the vanilla attention part, estimates put it at something like 70 to 80% of the total time you wait. 70 to 80%. So if you don't crack attention efficiency, you basically can't scale these models much further. It's the bottleneck.
It really is. And that leads us right into today's topic, native sparse attention, or NSA.
NSA, developed by DeepSeek AI and collaborators.
Right. And they're positioning this as, well, a comprehensive solution. It's not just one clever algorithm. It's pitched as this whole framework that integrates algorithmic ideas with, crucially, hardware-aware optimizations.
Aiming for actually efficient long context modeling, not just theoretically possible.
Exactly.
Now, the core claim, this is what really grabbed my attention. It almost sounds too good to be true. They're claiming NSA can match, or maybe even beat, full attention performance.
Right. Across the board, general tasks, long context stuff, even complex reasoning.
But at the same time, achieve huge speedups. Like, what was the number? Up to 11.6 times faster decoding at that 64K length.
That's the headline number, yes.
Yeah.
11.6x. It's
ambitious.
Ambitious is one word for it. Sounds almost like breaking the laws of physics for transformers.
Well, that's what we need to dissect today. Our mission, really, for you, our expert audience, is to go deep on this. Professionally unpack how they claim to pull off this dual achievement.
So beyond the flashy numbers, we need to understand the algorithms, the hardware tricks, and critically scrutinize the experimental results.
Exactly. Does this paper really solve the problems that have historically made sparse attention methods stumble in practice? That's the core question for this deep dive.
Okay, let's start unpacking that journey. Sparse attention, conceptually, it makes perfect sense.
Right. It's the logical approach instead of every query looking at every single key before it.
Which is the older dollar part.
Right. You just selectively compute the really important query key pairs. Reduce the overhead.
But as you said, the sources are pretty clear that historically these methods, they sound great in theory, but often fail when you try to actually deploy them. Why is that?
Yeah, it's this gap between theory and practice. Reducing the FLOP count, the raw number of calculations, it just doesn't automatically mean faster wall clock time. The NSA paper really nails down two big recurring challenges that have kept sparse methods from, delivering in the real world.
And the first one is about hardware, the difference between fewer calculations and actual speed.
Exactly. Hardware alignment. This is absolutely critical if you're dealing with GPUs and memory. It's not enough to just do fewer calculations if the calculations you do keep involve jumping all over memory.
So scattered memory access patterns.
Precisely. To get real speed up, you need a design that's explicitly hardware friendly. You have to think about tensor core utilization, making sure memory access is contiguous, smooth, both during pre-filling and decoding.
If your sparsity pattern messes up memory locality,
you kill your throughput, even with fewer FLOPs.
Okay, that makes sense.
Yeah.
And the second challenge, it's about training.
Right. It's about the training process itself. A lot of older methods tried to slap sparsity on after training a dense, full attention model, like a postdoc fix.
Prune it afterwards or something.
Kind of, but NSA argues you need a training-aware design. The sparsity needs to be baked in from the start, stable, end-to-end.
Why is that so important? Training with sparsity from the beginning.
Two big reasons. First, efficiency. You avoid paying that huge $N2 computational cost throughout the entire pre-training phase. That saves immense resources.
Okay, cheaper pre-training.
And second, performance. When you force sparsity onto a model trained with full attention, you can knock it off its optimal path. It hasn't learned to use sparsity effectively. This often leads to a noticeable drop in performance. NSA wants to avoid that sacrifice entirely by being native. #1.2, the illusion of efficient inference.
let's dig a bit more into why some specific older methods fall short during inference. The paper talks about something called phase-restricted sparsity. What's that about?
Yeah, this is about methods that are only efficient during one part of the whole LLM process.
Like good at decoding, but bad at the initial prompt processing.
Exactly. The example they give is H2O. It's apparently pretty good at making the autoregressive decoding part sparse, generating token by token.
Okay.
But it often needs this really heavy pre-processing during the pre-filling stage. When you first feed in the long prompt, it might need to calculate the full attention map anyway, or run expensive clustering up front.
Ah, so if your task involves loading a massive document,
Yeah.
lots of pre-filling, and then generating only a short summary, not much decoding.
Your overall speedup gets diluted, massively diluted, potentially. If one crucial phase is still slow, the total benefit just shrinks.
Especially for things like complex reasoning, chain of thought, which might involve both long context loading and long generation steps.
Precisely. These phase-restricted methods just aren't effective for those kinds of mixed real-world workloads.
Okay, that's one pitfall. The paper highlights another, maybe more technical one, incompatibility with modern architectures like GQA or MQA.
Right. Grouped query attention and multi-query attention. These are super important for inference efficiency now.
Because they share the key value cache across multiple query heads, reducing memory traffic, right?
Exactly. They're designed specifically to tackle the memory bottleneck. But this is where some sparse methods hit a wall.
How so?
Well, take a method like Quest as an example from the paper. It apparently selects the important keys and values independently for each query head.
Okay. Seems reasonable for standard multi-head attention.
It works fine there. But in GQA, you have a group of heads, say, 8 heads sharing one single KV cache.
Ah, I think I see where this is going. If each of those 8 heads picks a different set of keys.
The memory controller has to fetch the union of all those sets. So head 1 wants keys A, B, C. Head 2 wants keys B, D, E. Head 3 wants F, G, A.
The system ends up having to load A, B, C, D, E, F, and G.
Exactly. Even if each head only needed a few keys, the total number of keys loaded from the slow, high-bandwidth memory could still be huge. And worse, they're likely scattered all over the place, non-contiguous.
So even if you reduce the number of computations, the actual memory bandwidth needed stays high, maybe even gets worse because it's fragmented.
Precisely. It completely undermines the whole point of GQA-MQA, which is to minimize memory access by sharing that cache effectively.
Okay, so this failure, this incompatibility with GQA-MQA, it's a major blocker for practical sparse attention. NSA had to solve this.
It was a fundamental requirement. They needed a way to make the sparsity decision consistent across all heads within a GQA group. Hashtag 1.3, the myth of trainable sparsity.
All right, let's shift from inference problems back to training. You mentioned the need for native trainability, learning sparsity from the start. Why is just applying it post hoc after training so bad for performance?
The main risk is derailing the model. Performance degradation. Think about it. The model spent its entire training life optimizing its weights, assuming it could attend to everything.
Okay.
Then you come along and suddenly take away, say, 80% of its attention connections. Empirical results mentioned in the paper suggest that even the top 20% of attention scores only capture about 70% of the total attention weight or mass.
So there's still 30% of the signal spread across the weaker connections.
Right. And some of those weaker, long-tail connections might be really important for subtle things, maybe specific retrieval mechanisms, or how different experts talk to each other in a mixture of experts model. Cutting them off post hoc can break things.
Okay, so native training is better for performance. But people have tried to build trainable sparse attention before, right? What were the roadblocks?
Yeah, they've tried. But they ran into major technical hurdles. The first big one is using components that just aren't trainable, non-differentiable operations.
Meaning you can't use standard backpropagation to learn them.
Exactly. Gradient flow gets blocked. Think about methods like cluster KV, which uses K means clustering, or magic pig using simhash.
Clustering, hashing.
As.
Those involve making hard choices, right? This token belongs to cluster A, not cluster B.
Precisely. Those are discrete binary decisions. Is this key selected? Yes or no. You can't smoothly adjust that decision using gradients. So the model can't learn the optimal way to select tokens because the selection mechanism itself is outside the optimization loop.
The selection stays a fixed heuristic, it doesn't adapt.
Right. The second big hurdle, even for methods that are technically differentiable, is inefficient backpropagation. And this often comes back to memory access patterns again.
The hardware issue strikes again, but during training.
Exactly. But it bites even harder during training because of the backward pass. If you use a strategy that selects individual tokens, very fine-grained selection.
The cache intention, maybe?
Yeah, methods like that. The scattered memory access you get in the forward pass, you get the same problem, often worse when you need to gather gradients in the backward pass.
And this prevents using optimized kernels like flash attention.
Precisely. Flash attention and similar techniques rely heavily on accessing large, continuous blocks of memory to get high throughput on the GPU. Token granular sparsity breaks that assumption. You fall back to much slower, less efficient kernels, and your training efficiency just tanks.
Wow. Okay. So the constraints for NSA were incredibly tight. It had to be. Fully differentiable end-to-end, use hardware-friendly block-based operations for memory access, and be compatible with GQ-NQ day sharing.
Absolutely. It really forced a fundamental redesign, not just tweaking existing ideas. Okay, so before we get into the nuts and bolts of NSA's structure, let's just quickly frame the efficiency challenge using this concept of arithmetic intensity, AIR.
Right. AIR, that's the ratio of compute operations to memory operations, basically.
Yeah, FLOPS divided by bytes transferred. It tells you if your workload is limited by calculation speed, compute bound, or by memory speed, memory bound.
And for LLMs, the bottleneck changes depending on what you're doing, right?
Exactly. During training, or the initial pre-filling of a long prompt, you're usually doing big matrix multiplications across batches and long sequences. That's high AIR.
Lots of computation per byte loaded.
Right. So training and pre-filling are typically compute bound. The main goal there is just reducing the total number of calculations, getting rid of that all and $2 cost.
But then during decoding, generating one token at a time.
The picture flips completely. You have one query vector, and you need to compare it against the entire KV cache, which could be huge.
Very few calculations, but potentially massive amounts of data loaded from memory.
Exactly. Critically low AI dollars. Decoding is overwhelmingly memory bound, so the optimization goal shifts entirely. Now, it's all about reducing the volume of data you have to pull from the KV cache for that single token.
Okay. So NSA needed a design that could tackle both reduce computation for training prefill and reduce memory access for decoding. A unified approach.
That's the challenge they set out to solve. Hashtag tag 2.2. The overall framework and gating mechanism.
All right, let's look at how they actually built it. The core idea is replacing the standard attention on the full Thaler-Weiler matrices.
DT.
Right, replacing that with attention on some smaller, compact representation. TIL-DT.
Exactly. These TIL-DT are generated by some learned mapping functions, $5 and $5. That's the basic setup in equations 3 and 4.
But it's not just one single sparse calculation, is it? The paper mentions a hierarchical strategy, equation 5.
Correct. The final attention output, HOTRS, isn't from one sparse mechanism. It's actually a weighted sum, an aggregated, gated sum of 3 different parallel attention branches.
3 branches working together. What are they?
They label them SECR-WAM 5P SLC WIN.
Yeah.
That stands for compression, selection, and window.
Compression, selection, window. And they're combined using learned gates. Sigurd Winlow.
Yes, each branch, SECR-WAO, gets a gate score, Sigurd in 1. This score is calculated by a simple MLP followed by a sigmoid function, so it's fully differentiable.
So the model learns how much to trust each branch for any given situation.
That's the idea. The gating lets the model dynamically adjust the mix. Maybe for local patterns, the window branch gets a high gate score. For identifying broad topics, the compression branch might dominate. It allows flexible, context-dependent sparsity.
And the overall sparsity is guaranteed because the total number of keys and values used across all 3 branches in dollars is kept much smaller than the full sequence length dollars.
Exactly. That's the core constraint ensuring efficiency.
Okay, let's break down these 3 branches. Starting with the one that sounds like it's aimed at the compute-bound problem. Token compression. Hashtag tag 2.3.1. Token compression, coarse-grained.
Right. Token compression is about giving the model a kind of low-resolution summary of the history. It aggregates blocks of sequential keys and values into single compressed vectors.
How does it do that aggregation? Is it just averaging or something?
No, it's more sophisticated. It uses another learned MLP, which they call varfiller. This MLP takes a block of keys values, say 1L 322 tokens long, and maps it down to a single compressed representation till compute.
Okay, I'll learn decompression.
Crucially, they also include intra-block position encoding within that MLP.
Why is that important?
It means the compressed vector still retains some information about the order and structure inside the original block. It's not just a bag of words representation. This helps preserve meaning during compression. Equation 7 describes this.
And they use a sliding stride, $2, $16 hours, while the block size high under 3T2. Why overlap the blocks like that?
That overlap, 216 tellers is half of 1 on 3200, is important to avoid losing information at the boundaries between blocks. It creates smoother transitions. Information near the end of one block is also captured near the beginning of the next compressed representation.
So this branch gives a fuzzy, big-picture view of the context, significantly cutting down the number of keys values.
Exactly. It captures coarser, higher-level semantics while drastically reducing the computational load. Hashtag 2.3.2, token selection, fine-grained.
Okay, compression gives the big picture, but you might lose critical details. So the second branch is token selection for fine-grained information.
Right. We need to preserve some high-fidelity specific information.
But we already established that selecting individual tokens is bad for hardware efficiency, scattered memory access.
Precisely. So NSA makes a critical choice here. Block-wise selection. They select entire blocks of tokens, not individual ones.
Why blocks? What's the justification?
Two main reasons, tying back to our earlier discussion. First, hardware performance. GPUs love reading continuous chunks of memory. Accessing blocks allows for much higher memory bandwidth and better use of tensor cores.
Makes sense from an engineering perspective.
Second, there's empirical evidence. If you actually look at attention maps from standard transformers, the important scores tend to cluster together spatially. Nearby keys often have similar importance levels.
Ah, so selecting a whole block containing a few important keys is likely to capture other relevant keys nearby anyway. It's a reasonable approximation.
Exactly. It seems to be a good proxy that aligns with how attention naturally behaves while being much more hardware friendly.
Okay, but now the tricky part. How do you decide which blocks to select? We need an importance score, but we want to avoid expensive or non-differentiable methods like clustering.
This is where I think NSA gets really clever. They reuse information they already calculated for the compression branch. Remember, the compression branch calculates attention scores between the current query tortoises and the compressed keys to locate curs.
Yes.
NSA uses those intermediate attention scores as a proxy for the importance of the corresponding regions in the original sequence. It's described in equation 8.
Wait, so the score that tells you how important a compressed block is, they use that same score to decide whether to select the original uncompressed block that it represents.
Essentially, yes. Because the compression attention score reflects the relevance of that whole region to the current query, they leverage it to guide the fine-grained selection. And crucially, because the compression branch calculation is fully differentiable.
The selection process based on its scores is also differentiable. End-to-end learning.
Exactly. No need for separate clustering or auxiliary networks. It's efficient and trainable.
Okay, that's neat. But they mentioned the selection block size is different from the compression block size. How do they reconcile that?
Right. They need a way to map the importance scores from the smaller compression blocks onto the larger selection blocks. Equation 9 provides a formula for that, basically aggregating the scores from the constituent compression blocks to get the importance score for the larger selection block.
Got it. And finally, they had to solve the GQA problem, making sure all heads in a group select the same blocks.
Yes. To avoid that memory nightmare we discussed, the solution is straightforward. They aggregate the importance scores across all the heads within a GQA group. Equation 10 shows this summing.
So all heads contribute to a single shared importance score for each potential selection block.
Correct. PSLC is that shared score. Then they simply select the top non-blocks based on this shared ranking. They use 116 of 1,006 selected blocks in their experiments, equations 11, 12.
And because the selection is now identical for all heads in the group,
the memory controller only needs to load that single shared set of 11560 single self blocks from HBM. It makes the whole process GQA compatible and memory efficient. Hashtag 2.3.3. Sliding window, local context.
Okay, compression for global, selection for important fine-grained details. What about the third branch? Just a standard sliding window. Seems a bit basic.
It is basic, yeah. Just standard attention within a fixed local window. 1W 512 2 tokens in their setup.
Why include it, though? Don't compression and selection cover both global and fine-grained?
The rationale is about training dynamics and stability. Local patterns dependencies within the last 512 tokens are often the easiest things for a transformer to learn. They adapt quickly.
Okay.
The concern was that if local attention was handled within the selection mechanism, the model might just get really good at using the local window and never properly learn the harder task of using the compression and selection branches for true long-range dependencies. It could shortcut the learning.
The gradients would overwhelmingly flow to the easy local part, starving the global mechanisms.
That's the hypothesis. By explicitly isolating the local computation into its own separate branch with its own keys and values, they prevent this kind of gradient interference.
So the window branch handles the immediate vicinity, letting the compression and selection branches focus their learning capacity purely on the challenging long-range and sparse patterns.
Precisely. It ensures stable learning of all three aspects: local precision, global context awareness via compression, and retrieval of critical sparse details via selection. Then the gating mechanism learns how to best combine these specialized outputs. #tag, hardtag3, hardware-optimized kernel design.
All right, the algorithm sounds elegant, especially the differentiable selection and GQA compatibility. But you stressed earlier that algorithms alone aren't enough. That 11.6x speedup hinges on custom hardware kernels.
Absolutely. Theory needs to meet the metal. While the compression and sliding window parts can apparently reuse existing optimized kernels like Flash Attention 2, the sparse selection attention is the tricky one.
Because it needs to read these scattered blocks identified by the selection mechanism.
Exactly. Loading potentially $160 non-contiguous blocks efficiently requires specialized code. They implemented this using Triton, targeting NVIDIA A100 GPUs specifically.
So what's the core optimization? They mentioned standard flash attention groups queries temporally, but that doesn't work well here.
Right. Standard flash attention often processes a block of consecutive queries together, but for sparse attention, those consecutive queries might need completely different sets of KV blocks. You'd still have scattered reads inside the kernel's loops.
Okay, so NSA flips the script. How do they group things?
They use what they call group-centric data loading. It leverages the GQA structure.
Aligning the kernel with the GQA groups again.
Exactly. Figure 3 illustrates this. Instead of looping over query blocks, the outer loop of their Triton kernel iterates through query positions, $2. And for each position t, the first thing it does is load all the query vectors for all heads within a single GQA group into the fast SRAM.
Okay, load all queues for the group of position t. What's next?
Then the inner loop fetches the required key and value blocks, but crucially, it fetches the blocks identified by the shared selection index set, II-lollers, which is the same for all heads in that group.
So it loads the 16 selected KV blocks, (k), into SRAM just once for the entire group.
Correct. These loads are efficient because each of the 16 blocks is itself contiguous in memory. The kernel loads them sequentially into SRAM.
And because AT is shared, you avoid loading a same KV block multiple times for different heads in the group, minimizes HBM traffic.
Precisely. This group-centric approach eliminates redundant KV transfers. Once the shared queues and the shared KVs are in SRAM, the actual attention computation, matrix, multiplies, softmax, can happen very efficiently using standard optimized techniques within the Triton kernel.
So this kernel design directly exploits the GQA-compatible block selection mechanism they developed.
Absolutely. The algorithmic choice, shared block selection per GQA group, enables the hardware optimization, group-centric data loading in the kernel. This maximizes arithmetic intensity within the kernel, minimizes off-chip memory reads, and leads to the observed speedups.
The theory and implementation sound solid, but, the proof is in the pudding. Did it actually work? They tested this on a pretty beefy model, right?
Yeah, they didn't mess around. A 27 billion parameter GQA MoE backbone. That's mixture of experts.
So complex routing involved too? How many active parameters?
About 3 billion active parameters per token, 30 layers deep. GQA was set to 4 groups, 64 heads total. And the MoE setup was quite large. 72 routed experts, 2 shared experts, selecting the top 6 experts per token.
Okay, so this is being tested on a genuinely modern complex architecture, not some toy model. #tag 4.1, pre-training setup and stability.
Right, and the training was substantial too, pre-trained on 270 billion tokens of 8K length text. Then they did supervised fine-tuning, SFT, on 32K length text using Yarn to handle the context length extension.
Now for our audience, introducing a new complex sparse mechanism during pre-training, stability is a huge concern. Did NSA cause training headaches, oscillations, divergence?
Apparently not. The convergence curves shown in Figure 4 look really good. They report stable and smooth convergence even within that complex GQA MoE setup.
That's impressive itself.
But what's even more striking is that the NSA model consistently achieved lower pre-training loss values than the full attention break line trained alongside it.
Lower loss. So the sparse model actually learned better during pre-training.
That's what the data suggests. It feeds into this idea they mentioned later. Maybe the sparsity acts as a kind of architectural regularization.
How so?
By forcing the model to be efficient and focus its attention resources from the very beginning, maybe it helps the optimization process. Perhaps it filters out noise or prevents the model from getting distracted by irrelevant tokens, leading to a better final state. It's an intriguing possibility. Hashtag 4.2. Performance comparison on diverse tasks.
Okay, lower pre-training loss is nice. But what about actual downstream task performance? Let's start with the general benchmark, shorter context stuff from Table 1. How did NSA do there, where you wouldn't expect a huge efficiency advantage?
Surprisingly well, actually. They report NSA outperforming the full attention JUC line on 7 out of 9 standard benchmarks.
Which ones?
Including things like MMLU and CMMLU for multilingual knowledge, BBH for challenging reasoning, coding benchmarks like MBPP and Human Evil, and math reasoning like GSM-8K and math.
And they specifically call out gains on reasoning tasks, DROP and GSM-8K.
Yeah, plus 0.042 on DDROP, plus 0.034 on GSM-8K over the full attention baseline.
Now, I have to push back slightly here. Whenever someone claims an efficiency method also improves performance, the immediate suspicion is, was the baseline really optimized? Is it a fair comparison?
That's always the right question to ask. Based on the paper's description, they seem to have put effort into making the baseline strong. The explanation they offer for the improvement is interesting, though.
What is it?
They argue that because NSA is trained natively with sparsity, the model learns to focus on the most important information more effectively. It inherently filters noise. This enforced focus, they suggest, actually enhances its ability to handle complex tasks, especially reasoning where identifying critical information is key.
So the efficiency mechanism itself forces better learning habits on the model.
That's the argument, the architectural regularization idea again.
Okay. Let's move to the long context arena. That's NSA's home turf, the needle in a haystack test, finding specific info buried deep in 64K tokens.
Perfect score. According to Figure 5, NSA achieved 100% retrieval accuracy across all positions tested within the 64K context.
Wow. Okay, that's strong evidence for the hierarchical design working, isn't it?
It really is. It suggests the compression branch is successfully scanning the whole context to find the rough location, and the selection branch is preserving the fine-grained detail needed to pinpoint the exact needle.
What about broader long context tests? They used long bench, right? Table 2?
Yes, long bench covers a wider range of tasks, QA, summarization, coding, retrieval, all over long sequences. And they made sure to set the sparsity level fairly across different sparse baselines.
How many tokens were active on average for a 32K sequence?
Around 2,560 tokens, so quite sparse.
And the results?
NSA came out on top. Highest average score on long bench, 0.469. That beat full attention by plus 0.032 and another strong sparse method, exact top, by plus 0.046.
Again, beating full attention on its own game, essentially.
Particularly on the really complex reasoning tasks within long bench, things like multi-hop QA, they saw gains of plus 0.087 on HPQ, plus 0.051 on 2wiki compared to full attention. Also, strong gains on long code understanding, LCC, plus 0.069.
What do they attribute this success to?
Primarily that end-to-end training with sparsity, allowing the model to optimize the sparse patterns from the start, and also the effectiveness of the three-branch design balancing local, global, and selected information. Hashtag 4.3. Chain of thought reasoning, a benchmark.
They push the reasoning evaluation even further, right?
Yeah.
Using chain of thought on mathematical problems.
Yes, they fine-tuned both NSA and the full attention baseline, specifically on mathematical reasoning traces, creating NSAR and full attention R. Then they tested them on the A benchmark, which requires generating long, step-by-step derivations.
How did NSAR stack up against full attention R here? Table 3.
NSAR won quite significantly. At an 8K generation limit, it outperformed full attention R by plus 0.075. Even at a 16K limit, it was ahead by plus 0.05.
So even when given lots of room to generate, the sparse model performed better on complex, multi-step reasoning.
Yes. It suggests NSA is better at capturing those long-range logical dependencies needed for mathematical proofs and derivations. It seems to use its context more effectively.
The paper includes a specific example in the appendix, contrasting the reasoning process of NSAR versus the baseline on a logarithm problem. Let's dig into that. Sounds insightful. What did the baseline's reasoning look like?
The full attention baseline. Well, it got the right answer eventually, but the process was really convoluted. Even with the 16K token limit, its thought trace ballooned to over 9,000 tokens.
9,000 tokens for one math problem's reasoning.
Yeah. And structurally, it struggled. It started with one approach, variable substitution, got stuck, basically admitted it might not have a solution, and then had to pivot its entire strategy. It resorted to using things like matrix inversion and Cramer's rule, quite heavy machinery, to finally grind out the answer.
So lots of wasted effort, dead ends, and computationally expensive detours. How did NSAR approach the same problem?
Much, much cleaner. Its entire thought trace was only about 2,275 tokens, less than a quarter of the baseline's length.
And the reasoning structure.
Far more direct and efficient. It stuck to a single, focused substitution path, converted to exponential form smoothly, and derived the $6 Yzito values without any major strategic shifts or needing those complex linear algebra methods.
That's a striking qualitative difference. It's not just about fewer tokens, but a more coherent, less brittle reasoning process.
Exactly. It really suggests the sparse architecture isn't just faster. It might actually enable more robust, focused, and efficient thinking over long chains of reasoning. It avoids getting lost in the weeds, perhaps because it's forced to prioritize important steps. Hashtag 4.4, computational efficiency.
Okay, the performance side looks remarkably strong. Let's nail down the efficiency numbers again. Training first the compute-bound phase. How much faster was NSA compared to Flash Attention 2?
The gains increase significantly with sequence length, which makes sense. Figure 6 shows that at a 64K context length, NSA achieved up to 9.0 times faster forward pass and 6.0 times faster backward pass compared to a Triton-based Flash Attention 2 baseline.
9 times faster forward pass. That's huge for training throughput. It really validates that hardware-aligned kernel design, doesn't it?
It does. Maximizing tensor core use, blockwise access, smart loop scheduling, it all paid off in the high AI either compute-bound regime.
Now, decoding, the memory-bound phase. This is where that headline 11.6 next number comes from. Why is the speed up so much larger here?
Because decoding speed is almost purely dictated by how much data you have to load from the slow HBM high bandwidth memory. It's all about memory access volume in this low AII regime.
Okay, so how much does NSA actually reduce that memory access volume?
Dramatically. At a context length of 65,536, full attention has to load all 65,536 tokens worth of keys and values from the cache. NSA, with its 3 branches, only needs to load the tokens in the sliding window, 512, the compressed tokens related to 64K 16 stride, and the 16 selected blocks, 1664 was 124 tokens. The paper states the total equivalent is just 5,632 tokens.
Wow. From 65,536 down to 5,632, that's what, like a 12-fold reduction?
Almost exactly, about a 91.5% reduction in the data loaded from HBM.
And because decoding is memory-bound, that reduction in data loaded translates almost directly into speed up.
Exactly. Less data to load means less time waiting for memory. That 11.6x reduction in memory volume leads directly to the expected 11.6x speedup in wall clock time for decoding at that 64K length.
It confirms that the whole GQA-compatible group-centric selection and kernel design really cracked the memory bottleneck for long context decoding. The efficiency gain just gets bigger as the context grows.
Precisely. The benefits amplify significantly at longer sequence lengths.
You know, one thing I appreciate about this paper is that they don't just present their final solution. They talk about the dead ends, the strategies they tried that didn't work. That's often just as informative. Hashtag 5.1. Challenges with abandoned token selection strategy.
Absolutely. They discuss trying key clustering approaches like cluster KV, and they ran into some serious problems.
What kinds of problems?
Well, first, just the raw computational cost of doing dynamic clustering during training was too high. But maybe more critically, especially for their MOE architecture, the clustering often resulted in really uneven groups.
Meaning some clusters got way more tokens than others.
Yeah, and that creates terrible load balancing problems for the mixture of experts layer. Some experts would be overloaded, others idle. It kills parallel efficiency.
So even if clustering reduced average FLOPs, the slowest expert path determined the overall speed, making it inefficient in practice.
Right. Plus, these methods had practical headaches, like needing periodic reclustering, complex training setups. Just not ideal.
They also looked at other ways to do blockwise selection scoring, right? Before landing on reusing the compression scores.
Yes, they explored a couple of alternatives. One was inspired by ideas like seer attention, using an auxiliary loss. It involved extra queries, trying to supervise the selection using KL divergence against some reference.
Did that work?
Not really. It added extra computational overhead, and worse, Figure 7 shows it actually resulted in higher training loss than NSA. The auxiliary tasks seem to interfere with the main learning objective.
Okay. What was the other alternative? Something parameter-free?
Yeah, heuristic selection may be similar to the quest strategy, basically directly calculating importance based on some simple product between query and key chunks.
Simpler, but how effective?
The main issue was low recall. It just missed too many important blocks. And again, Figure 7 shows this heuristic approach also had significantly worse training loss compared to both full attention and NSA.
So these comparisons really highlight why NSA's approach using the compression scores as that differentiable proxy was so crucial.
Exactly. It neatly sidestepped the non-differentiability of clustering and the performance degradation or low recall of the other methods. It found that sweet spot of being trainable, efficient, and effective. Hashtag tag 5.2. Attention map visualization.
And finally, they bring it back to that empirical observation that motivated the blockwise design in the first place, the attention map visualization in Figure 8.
Right. Looking at a heat map of attention scores from a standard, pre-trained, full attention model,
What does it show?
it clearly shows that attention scores aren't randomly scattered. They exhibit this distinct blockwise clustering distribution. Keys that are close to each other in the sequence tend to have similar levels of importance to a given query.
So there's an inherent spatial locality or continuity in the attention mechanism itself.
Precisely. And this empirical finding provided strong justification for their decision to operate on continuous blocks of tokens, rather than trying to pick out individual scattered tokens.
Because selecting a block is likely to capture a whole region of similar importance anyway.
Yes. It aligns with the natural structure of attention, while also being way more efficient for the hardware enabling contiguous memory access, better tensor core use. It's a really nice example of letting empirical observation guide hardware-aware algorithmic design. Hashtag tag outro. So wrapping up this deep dive, native sparse attention NSA really does seem to offer a compelling path forward for LLMs that are hitting that quadratic wall with long contexts.
It tackles those two core historical problems of sparse attention head-on.
Right. Integrating sparsity natively right into the training process, avoiding performance degradation, and ensuring the design is truly hardware-aligned for efficiency across the board, pre-filling, decoding, even the backward pass during training.
And the outcome, as we've discussed, appears to be this remarkable dual achievement. On one hand, significant computational efficiency gains that 9x in training, up to 11.6x in decoding at 64K.
And on the other hand, not just maintaining, but actually enhancing modeling capability, outperforming full attention and other sparse methods on benchmarks, especially those critical long context and complex reasoning tasks.
It really challenges that old assumption that efficiency must come at the cost of performance. NSA seems to show you can potentially have both.
Which brings us to a final, maybe provocative thought for you, our listener. Given this evidence, especially the finding that NSA's native sparsity seems to force the model into a more focused, effective representation, leading to better reasoning, does this signal a turning point? Could it be that the future of truly capable, scalable LLMs requires us to move beyond full attention entirely, to embrace sparsity not just as a necessary evil for computation, but as a fundamental tool for architectural regularization, a way to build models that learn more robustly and focus more effectively from the start?
So is sparsity the optimization, or is it actually part of a better architecture?
That's the question to ponder. Is dense attention potentially holding models back in a way? Something to think about as you design your next long context system.